two, 1 2, 1 2, 1 2. Hey, hey.
Eventually that adds up to if a whole group of people, say on a cruise or a work trip, get sick, it causes economic burden eventually.
Okay.
Also for younger children and elderly, it is quite severe and can be fatal.
Okay.
Which is why the vaccine is also we're trying to push as much.
Okay. I see. So cholera will be the extreme of this type
I
of.
think cholera is
bacterial, yes.
So I don't really work on bacteria, so I'm not sure the extremities. But in terms of viruses, this one is the most extreme of the gastrovirus.
Okay.
Especially in people of all ages.
Yes. Oh, very good. Interesting. So what do you think is the solution to at least try and reduce the load, the viral load in our water system?
I honestly think that we need to improve on our sanitation and clean water around the country, because this is mainly transmitted by the fecal-oral route.
Yes.
And contaminated water is a big issue. In shellfish, in lettuce, even in, it's not only to say, when I open the tap it's dirty and I'm drinking that, no. It's also throughout the foods and stuff like that. So I do think our sanitation needs to improve.
How does it compare to other countries, for instance, like developed countries? Do they also have a similar problem, or this is only for
countries
like ourselves?
Yeah, no, it is more for the low to middle income countries, but it's not to say that other countries don't have it. There's a lot of outbreaks in the countries of cruise ships and childcare centers, like those environments. So in the US, there was a massive outbreak a few years ago for the cruise ships. And everyone got very sick because now they want fancy oysters and then they don't clean the oysters. So it's not only in developing countries, it's just more predominant and the prevalence is much higher here as compared to there. And I do think our surveillance needs to improve, which is what I'm trying to do. Because surveillance, the more we know about it, the more we can treat this.
Thank you very much. Nice meeting you. Good work.
Hello. How are you? Nice to meet you. How are you?
So the policy is the supervised learning, which is an artificial intelligence system whereby it consists of categorical and lab-based data. So first of all, we start by collecting the data set, and we collect our data set from different open databases such as the Materials Project Database, Materials Descriptor Property, and after collecting our data set, we clean it. So in our study, we collected about over 168,000 sodium-containing materials. Then after that, we extracted features like ionic cracking, ionization, and then we tested several algorithms, including the physics-based model such as the generative adversarial network and neural network. And we also tested the black box models such as the random forest and gradient boosting. Then after building our model, we go to model validation and evaluation, whereby we check the performance accuracy of our model. Then we use the evaluation indices like the normalized difference correlation and the weighted balance accuracy as our evaluation indices. So to check the performance of our models, both the normalized difference correlation and the balance accuracy should be the score should be saturated to indicate that the model is performing accurately. Then after that, we fine-tune the model using multi-tuning as hyperparameterization to boost performance. And after that, we go to material design. So here is a framework to show how we generated the new materials. That is how the expression state of several elements. So we used the generating adversarial network to generate the new sodium ion materials based on information state balance. Then the algorithm reaches to capture this value by showing an equation that balances the total positive and negative charges of the compound. Then we go to simplify the most optimal features for predicting the as the most important features. Our crystals after that we have the correlation basically it's just a visualization which shows like we have place based with our 168,000 materials. Then after that we go to model performance where we check the target properties, how each robot performs predicting of target property. So we have the target then we can see that another database that is we have However, we noticed to the rarity of the data set in the triclinic. Then we also go to class-wise performance in predicting our crystallographic symmetries. So the true negative and true positive shows the data that was correctly classified, and then the false negative and false positive shows the data that was misclassified. So our random forest model was found to be the best in predicting the crystallographic symmetries, and this can be justified by the weighted methods correlation coefficient ranging from 0.88 to 0.9, and also the weighted balance accuracy ranging from 0.93 to 0.95 for the target variables. Then in conclusion, I can say we have successfully developed and validated the machine learning algorithm whereby we managed to predict the crystallographic symmetries using composition, and besides predicting the properties, we managed to generate hypothetical sodium-ion battery materials, which paves the way for materials discovered. And I would like to acknowledge the following parties, especially the CSIR Inter-Bursary program for funding.
The CSIR, which program was that?
The IBS,
Oh,
Inter-Bursary.
Inter-Bursary. I see. Okay, very
Thank
good.
you.
No, excellent. Which year are you doing now?
It's my second year.
The second year. Okay, how far are you from completing your PhD?
I'm currently in the writing process.
Okay, excellent, excellent. No,
So
well done.
I'm still going to verify the novelty of our materials.
Okay, okay, okay. Wow, no, very impressive. This model that you've developed can only be used for sodium.
No, it
Can be applied in other materials as well.
It can be applied
Okay.
in lithium. When I was doing honors, I was focusing on lithium-ion batteries.
Ah, okay,
Yes.
okay.
Then we moved to sodium-ion batteries, looking at that with lithium-ion batteries,
Yes.
it is not that environmentally friendly compared to the sodium-ion batteries.
Okay, okay, okay. No, excellent. Well done. Congratulations.
Thank you.
Good luck with the rest of your studies.
Thank you.
Very good. Thank you.
Thank you.
Let's just watch our time. What time is it now? Okay, we've got 5 minutes. Hello, ma'am. How are you?
I'm good, how are
I'm
you?
Tulan Dlamini.
I'm Bridget Kaweko.
Nice meeting you.
Nice to meet you.
Very good. So what are you working on?
We have a lot of photovoltaic solar cells out there.
Yeah,
Some
yeah.
are sodium lead based, perovskite lead based, and then these hybrid organic and organic perovskites.
Okay.
So, but the problem with these ones that are there in the market right now is that they have toxicity, like toxicity, and they have moisture sensitivity, and they're environmentally unfriendly, so they can't be widely commercialized. So we are working with perovskites that are all inorganic halide perovskites that are going to help us to improve the power conversion efficiency of those now going on solar cells. So we were using the DFT, which is density functional theory, to calculate our properties that we're going to use to characterize our material for the photovoltaic applications. So we found out that the lattice parameters that we calculated agree very well with our literature, and that both our materials that we're working with are mechanically stable and that they're ductile, and that the electron band gap that we're working with is the exact one that we are trying to get when we are looking for photovoltaic applications, and that our material is also reflective and it also can absorb light and then turn it into electricity.
Oh, very good. Very
Yes,
good.
that's basically what we're trying to
No, excellent. What are you studying?
do. I'm studying
Which year are you in?
my first year master's,
First year master's. Oh, okay, excellent. So where are you studying?
University of Limpopo.
What did you do for your undergraduate?
I did almost the same thing in my honors, yes.
Okay, physics or
Physics.
Physics.
Yeah.
Okay, no, excellent.
Yeah.
Excellent, excellent. No, well done and good luck with the rest of your studies.
Thank you so
Looks
much.
very exciting.
Thank you.
Great work. Very good. Okay. I think there's one more, then we go. All right. Okay. Hi, how are you?
I'm good.
Very good. I'm Tulan Dlamini.
I'm Justin Safari.
Nice meeting you, Justin.
Yes.
What are you working on, Justin?
Okay, I'm working on immobilization of enzymes.
Okay,
So
from Rhodes.
enzymes, yes, I'm from Rhodes University. Enzymes are used in many industries to produce many products.
Yeah, yeah.
But the problem with the enzymes, you cannot use them 2 times. You use them 1 time and then you need to denatured. So then it's not good for industry. So what we are looking at immobilizing them so that we can use them more than 1 time. And what we are immobilizing them, or we are immobilizing them on magnetic nanoparticles, so that we can run the first reaction and remove them with a magnet and run a second reaction and number of reactions. So in our work we are looking at textilanase, that is an enzyme that has a lot of interest in the food industry, in the paper industry and the biofuel industry. And we are mainly looking at the food industry, where we are targeting a polymer that is in animal feed, and then we use the enzyme to pre-digest it for some animals like pigs or chicken that cannot digest that polymer. So far what we have done, we've immobilized them and we have tested the enzymes in many animal feeds.
Okay.
We were able to run the reaction more than 10 times and we are still keeping the activity. So we've improved the...
Wow. 10 times?
Yes, we did like 12 times and
This
we
is-
still have...
The activity remains the same.
Yeah, no, it was dropping a
Oh,
bit,
okay.
but
But
after
still.
like we still have like more than 50%.
Okay,
of
okay.
the
So if
activity.
we add, you have to add
Yes.
only 50% of what
Exactly.
you would have used previously.
Exactly, yeah. So that is it.
Okay.
So then we did characterization of the different products that are produced in there.
Fantastic.
And now what we are busy with is now testing the antioxidants, the increase of the animal's growth of the feed that you digest.
Ah,
Yes,
excellent,
that is it.
excellent. No, well done, well done, well done. Is he still alive?
No, he passed on.
He was in
my
my
main
class.
supervisor.
Is
And then when he passed on, then Prof HK is now the main supervisor.
I see. I was in the same class with him.
Yeah, okay.
Sure. He was a good man,
Yes,
Roy.
very, very good.
Sure.
Yes.
What happened? Was he ill?
No, he was in Stellenbosch for a conference, and then he had a heart attack.
Oh, really?
Yes. It was
That's
a
such a
surprise for all
pity.
of us.
Yeah, I know him very well. I mean, him and I studied together from first year all the way to PhD.
Yes. Yeah. He was my supervisor for masters and now for PhD as well. And then he passed on in the journey.
No,
Yes.
it was nice meeting you.
Thank
All
you.
the best. All the
Sure,
best.
sure. Thank you.
Can I give this back to you?
Let us all settle in as we start our program. Colleagues, the executive committee members present, and our researchers, good morning and welcome to, allow me to welcome you all to our 8th Emerging Researchers Symposium 2025 under the theme 8 Years of Innovation. My name is Lehlohonolo Tau and I will be your host for the day. As a homegrown Google search engine researcher myself, I have quite a lot of bits about research. I know a lot about research. So I am going to allow you then to lead our discussion and help us understand what research is about. As we settle down. We appreciate your presence and commitment to advancing scholarship and knowledge. And without further delay, allow me to call upon Jobe to take us through the safety briefing for the day.
Thank you, Program Director. Good morning, ladies and gentlemen. Welcome to the ICC. All protocol is observed. My name is Jobe Mkachwa, Safety and Setup Coordinator. In case of an emergency, please do not panic, do not run. Let's evacuate in an orderly manner using the two exits. Can use that one as well, towards the reception area. As you step out of the reception area towards your right, that's where the assembly area is. We have our emergency team on standby to assist you. Please remain in the assembly area until you're given further instructions. In case you're not feeling well, please note we have paramedics on site to assist you. Please also use the sanitizing stations around the area. The operation facilities, we have signage on site. Please also note, for security purposes, be on the lookout for your personal belongings, as this is a public building and we might have other delegates making use of the venue. For security reasons, as you going out of the gate, the security might ask you to switch on and off your vehicle to verify ownership. As Gasfontein is the area, if you're driving a Toyota, Fortuna, a Cross, that's what they steal most. Then we have a free Wi-Fi, no password required. Please feel free to use it. Enjoy the rest of your session. Thank you very much.
Thank you, Jobe, for the safety briefing. Unfortunately, I only drive a Kia. All right, allow me to proceed with the program for the day, which promises to bring to us insightful presentations from our researchers and meaningful discussions. At this time, I will call upon and welcome our CEO, Dr. Thulani Dlamini, to give us his welcoming address.
Thank you very much, Dihlaonolo. Members of the CSIR leadership and colleagues, our distinguished guests from science councils and higher education institutions, emerging researchers, members of the media, ladies and gentlemen, good morning. Good morning. Good morning. Yes, that's how young people talk. And a very, very hearty welcome to all of you to the CSIR. I had the opportunity to talk very briefly with some of the young researchers who have posters before the start of our session this morning. And I must say that I was very impressed by the depth of science and the quality of the work that I was exposed to. I only had the opportunity to speak to four researchers, but the quality of the work is really very, very impressive. And I'm sure that your work as well, even though I was not able to get to it this morning, is of the same quality. I think it fills one with a sense of hope and pride to see the work that you are doing. So as I stand before you this morning, I don't just see young researchers and engineers. I see dreamers, builders, and visionaries. I see the future of South Africa sitting right here in this auditorium. You, the young minds of our country, are the ones who will shape the next generation, who will shape the next chapter of our story. The next 8 years of touching lives through innovation, which is what the CSIR does and what the CSIR stands for. This symposium is not just another event in the calendar of the CSIR. It is a celebration of potential, a recognition that the boldest ideas often come from fresh perspectives. And I saw that this morning with, as I said earlier, the work that the colleagues shared with me. It is also an affirmation that the next generation of researchers will develop solutions to challenges we have yet to imagine. This symposium provides a platform to showcase the remarkable work, thank you very much, the remarkable work being done by emerging researchers at the CSIR as well as in our partner institutions. For 8 decades, the CSIR has been a home of pioneering science, technology, and innovation. And as we celebrate this legacy that we've built over 8 years, we also accept and recognize that the story of the CSIR for the next 8 years will be written by you, the emerging researchers. So the responsibility now rests with your generation to take forward this tradition of excellence, to define the breakthroughs of tomorrow, and to ensure that science remains a force for good in society, particularly now, given what we see happening in the rest of the world. As some of you would know, the CSIR was established in 1945 with a very clear mandate to serve the nation as a scientific powerhouse, driving cutting-edge research and technological innovation. Over the past 8 decades, we have achieved many bold scientific breakthroughs and industry-defining advances, and I can name many of those. Our work has laid the foundation for new industries and contributed to the creation of a capable state. From the beginning, innovation has been at the heart of who we are as a CSIR, and it remains central to our long-lasting legacy. As most of you would know and agree with me, the process of innovation is not trivial. It is fraught with many challenges and obstacles, and I'll say a bit more about this later. But I would like to reflect on 4 elements that make innovation truly meaningful. And these elements are purpose, collaboration, impact, and vision. The process of innovation must begin with a very clear purpose, whether it is a challenge to be overcome, or a need to be met, or a vision to be pursued. The second element of collaboration, which is, by the way, one of our values here at the CSIR, makes us realize that nothing that is transformative can happen in isolation. Collaboration is the lifeblood of innovation. And one of the key reasons this symposium exists, to encourage knowledge sharing, partnership, as well as co-creation amongst researchers. At the CSIR, collaboration is part of our DNA. We always say that everything that we do at the CSIR, we don't do it for ourselves, but we do it to create better society. We do it to create better government. We do it to support the development of our industries. We work across disciplines, institutions, and borders to tackle very complex challenges. The third element is impact. Innovation without impact is incomplete. As researchers and innovators, our responsibility is not only to create knowledge, but also to ensure that it makes a tangible difference, strengthening communities, improving lives, as well as building a better tomorrow for all of us. The fourth element is vision. And as young researchers, you must have big dreams. Albert Einstein once said, if at first the idea is not absurd, then there is no hope for it. Bold, unconventional ideas often spark breakthroughs that change the world. This is your moment. The CSIR remains a hub where ideas take flight and innovation becomes impact. We believe that young people are the key to rebuilding and transforming our country. We live in a time of extraordinary transformation. The world that we live in is volatile, it's uncertain, it's complex and ambiguous. Technologies like generative artificial intelligence are rewriting the rules of science, engineering, and innovation. And these are not just tools, they are multipliers of human potential. Generative AI is assisting us write reports, analyze our data, simulate experiments, and even suggest new research directions that we ought to pursue. So we must embrace the potential that technologies like generative AI bring to us. But here's the truth. Artificial intelligence will never replace your creativity, your curiosity, and your courage. It can only amplify it. Through your work, you are not just solving technical problems. You are solving national challenges and creating a better world. You are building resilience, sustainability, and prosperity for millions of South Africans. When you develop new materials, I heard this morning, the new battery materials being developed, for instance, at the University of Limpopo, or new enzymes that are being developed, or new ways of stabilizing enzymes to make sure that they can be used again and again in various processes. When you do these things, you are building new industries. When you develop models that tell us a bit more about climate systems, you are protecting communities. When you innovate in health, energy, and infrastructure, you are rewriting the future of our country. And now, with artificial intelligence by your side, you can do these things faster, smarter, and bolder than ever before. Therefore, I challenge you. Be fearless. Be relentless. Push boundaries. Ask bigger questions, questions that we couldn't ask because of the limitations that we had to work under. Be united. Collaborate across disciplines. Share your knowledge. Lift each other up. You are the architects of tomorrow. You are the ones who will take the CSIR and, of course, South Africa and the rest of the continent into a new era of innovation. So dream big, build boldly, and never forget, the future is not something we wait for. It is something we create. As I said earlier, I'll say one or two things about the challenges of being a researcher. So as I close, I'm reminded of a story of a young researcher like yourselves who submitted a paper to a journal for publication. And after waiting for a few months to get comments about his paper or her paper from the reviewers, finally received a very short report with only 3 sentences. So the report said, this article contains a lot that is new and a lot that is true. However, all that is true is not new. And all that is new is not true. So I hope that you'll get better reviews for the publications that you are going to write. So ladies and gentlemen, I hope that you've enjoyed the first day of the CSIR Emerging Researchers Symposium and wish you all the best today and hope that you'll use this opportunity to build new bridges, to create new connections, and to engage with each other in a spirit of collegiality and collaboration. Thank you very much for supporting our symposium. Thank you.
As Dr. Dlamini said it, that the boldest ideas come from fresh perspectives. Let us continue to foster knowledge sharing to build a better tomorrow for the future. Thank you, Dr. Dlamini, for your welcome note. Another round of applause to Dr. Dlamini. As we move on with our program, allow me to introduce and call upon Dr. Kelvin Mpofu and Dr. Masikole Lungolo, apologies for butchering your names, to help us go through the next segment that allows us to to listen to the session 4 cohorts that are about to present to us. To our presenters, please be cognizant of the time. You have 20 minutes allotted to your presentation, and inclusive of that, you have 5 minutes for a question and answer segment. Over to you, Dr. Masikole.
Good morning, colleagues. Thank you, sir. My name is Masikole Lukongolo. I'll be a co-chair this morning. My colleague, Kelvin, is held up somewhere, but he's going to join us shortly. So to start up this session, I would like to invite our first speaker, who is the researcher at the CSIR, as well as the PhD student, Londiwe Mutibane, who is going to talk to us about the sound transmission of additively manufactured microclear prostheses. Over to you, sister.
Good morning, everyone. As introduced, I am Londiwe Mutibane. I'm a researcher here at the CSIR within the laser-enabled manufacturing group of the Photonics Center. I'm also a PhD student in the field of materials engineering with the University of Cape Town. This morning, I'm going to speak to you about ears, and I hope that you will lend me yours. So the human ear is divided into 3 regions. There's the outer ear, the middle ear, which will be the focus of my talk this morning, as well as the inner ear. So as I'm speaking to you right now, sound waves are going through the air, and your earlobe is capturing them and channeling them through your ear canal, and they are causing what we call your eardrum. It's the tympanic membrane to vibrate. That vibration is translated to these 3 little bones, which are called the ossicles, and they too vibrate and make contact with the cochlea. The cochlea then decodes the sound vibrations, sends it to your brain, and says, she's talking to you, and you can perceive what I am speaking to you about. Now, when we speak of hearing, there's 2 aspects to it. There's the loudness of the sound, which is measured in decibels, and then the pitch of the sound, which is in the frequency scale or the hertz scale. And this is what I'm going to be speaking to you about. So in the infrasound range, which is the lower range of frequencies, you get animals like the elephant we see there. Elephants can hear in the lower frequency range as low as 5 hertz. On the opposite end, on the higher end of the frequency scale, that's where your bats, for an instance, can hear sounds up to frequencies of 120,000 hertz. With us, though, the humans, our hearing range of frequency is between 20 and 20,000 hertz. Now, hearing loss is a global challenge, and it affects the global population, about 8 to 20% of the global population. This is according to the World Health Organization. And this challenge often leads to the isolation and often dependency of the affected population. Of this affected population with hearing loss, conductive hearing loss affects about 55% of this population. Conductive hearing loss is when there is a break in the chain of your middle ear. If you look onto my slide again, the middle ear is made of your tympanic membrane or eardrum. These 3 bones that are known as the ossicles collectively, but individually it's the malleus, the incus, and the stapes, and then the oval window. So then whenever there's a break in that chain, we call that type of deafness or hearing loss conductive hearing loss. And this results because of things such as ear infections, birth defects, as well as blunt and sharp traumas. What's in place at the moment is that then they would reconstruct your middle ear or your ossicular chain through surgeries. The ENT specialists are what would do that. And they would replace either all 3 bones using what we call total ossicular replacement prosthesis, or often just the stapes bone using partial ossicular replacement prosthesis. Now, these prostheses can be made from different materials, including platinum, titanium, nitinol, and the likes. And they come in various forms or shapes. But there's been very little improvement in their design to simulate the ossicular chain in the last 50 years. They have challenges with poor stability, which results in dislodgements and then migrations of these prostheses. And as you can imagine, that's quite painful for the patient, and then you need to go in for a revised or a revision surgery to bring it back and put it in place. They also recover sound, but not as well as what your normal hearing would be. So if we look at the human ossicular chain, there it is. And this is one of the commercially available ossicular prostheses. And if you look at it, or look at them, they're quite different. So there's a great need for prosthesis designs that simulate the ossicular chain in shape, in size, and in their movement. And this is where additive manufacturing, also known as 3D printing, comes in. With this technology, we're able to fabricate components that are complex in their design and precise in the features that you can make. And so with this technique, we're able to fabricate prostheses that are similar in shape and size to the ossicular chain. One man who's done this is Professor Mashudu Chifularo, who is an ENT surgeon, and he pioneered the world's first middle ear surgery using 3D printed bones or 3D printed prostheses. And we are now currently working with him to further develop, this is his design, which he holds a patent on, to further develop his designs and also then look at the type of materials that can be used for these prostheses. And so what we've done on our side is print this design in 3 different materials. And this work actually was accepted by the CSIR TD panel at TR level 5. And so what I'm presenting to you today is the comparison of the sound transmission now of these prostheses. They need to be able to transfer sound from your eardrum to your oval window. It's a comparative study of these 3 3D printed ossicles made from 3 different designs. The prostheses, you can see them there, were manufactured in the materials of titanium 6-4, the ELI, which is the medical grade material, in nitinol, as well as platinum. They were fabricated using laser powder bed fusion, which is an additive manufacturing technique. And this was done at optimized parameters for each material. Now, to measure the sound transmission of these prostheses, this is guided by the international standard ASTM F2504-5. And what this standard says is it puts out how you are to measure your sound transmission. And so the setup is roughly, there's a speaker side where you would be inducing sound, and that sound should go through some form of an ear canal, eardrum, and then the ossicle or the prosthesis that's under the test would be there. I did something, okay. You have your oval window there, and then we use laser Doppler vibrometry. That's the technique. The vibrometer measures vibrations. So like I was telling you, sound is in waveform, and it's in the vibration of those, it's in the vibrations where you can measure whether sound is being transferred or not. And with this method, it is the middle ear transfer function that we are interested in. And this is the ratio of the velocity or the speed at which your prosthesis vibrates at the end over the sound pressure level that you are inputting. This was our laboratory setup, and as according to the standard, you have sound input, you have your prosthesis, and then you have your laser Doppler vibrometer. This is just the side view of it, and I think you can see it a bit better. There's the speaker. Here's the eardrum, the simulated eardrum. Here's the prosthesis, the oval window, and then there's the laser head measuring right there, measuring vibrations right there. So that was what we were doing, inducing sound at different frequencies. Remember at the beginning I said we hear at a range of frequencies, and here we were testing these prostheses at the range of frequencies for human hearing. It's sort of, as you heard, it's sort of like when you go for your ear test and you sit in a little box and they say you must press the little button when you hear the sound. It's something similar to that. So the analysis of the results was done on the DAC system. We were looking at the exciting frequency range of 400 to 4,000 hertz at 100 hertz intervals. The signals were pre-processed using Fourier transforms and analyzed using a MATLAB written software. We did 10 runs at each excitation frequency. Now coming to the results. On this graph, we're looking at the vibration which is measured in speed or velocity, right at the end at your oval window. And when we look at it, firstly, we can see that the nitinol is in the orange, the platinum is in the yellow, and the titanium is in the blue. In the first range, between about 400 hertz to 2,500 hertz, generally, the prostheses all have a similar trend. They go up at certain frequencies, go down at certain frequencies. What we also can note from here is that the nitinol prosthesis, which is the orange, is above these ones mostly, above the other two mostly. And at 2,500, we note a big change in the trend where now the nitinol sound transmission level goes way up while the other two decrease all the way down to 4,000 hertz. This graph shows now the middle ear transfer function, which is what I was saying the standard looks at. And again, here we see that the three prostheses generally have a same trend, and at 2,500, we have that phenomenon where the nitinol shoots up while the other two decrease. We also then compared our sound, or the sound transmission of our prostheses to literature as well as international standards, because that's the guideline. The ASTM standard is in the green. There it is. Thank you. And then what we see from here is that the nitinol, which is the orange, is mostly above the ASTM standard. The titanium, which is in the blue, is a little bit lower than the standard, but is mostly comparable in most frequencies, while the platinum in the yellow is above the standard mostly. So in conclusion, sound transmission was assessed using laser Doppler vibrometry on AM-produced prostheses. All the prostheses demonstrated effective performance across the human auditory range. The nitinol prosthesis we saw showed the highest sound transmission, followed by titanium and then platinum. At 2,500 hertz, we saw a significant change in the trend where the titanium and the platinum sound transmission sort of filters off down to 4,000 hertz, while the nitinol one displayed a sharp increase up to 4,000 hertz. We also demonstrated that the nitinol prosthesis has better sound transmission than literature findings as well as ASTM standards. And so the next step in this journey is that these validated prostheses would go into somebody's ear as the professor is busy with his clinical trials, or the next step are for him to go into clinical trials. And we are excited, as the CEO was talking about impact. Innovation needs to have impact because this is people's lives that are changed. It's someone's hearing restored. So I'd like to just acknowledge contributors to this work, the DSTI for funding through the CPAM program, the equipment that we used here at the CSIR, our industry partners, as well as our tertiary institution partners. Finally, just the team. This was a collaborative effort between different groups of the Photonics Center, LEM, national programs, novel lasers, and then also the industrial centers group, which is also still under the manufacturing cluster. And then lastly, just a mention of Mr. Waldo van der Westhuizen. He's the gentleman on the furthest right. Waldo was a critical member of our team, and he did some great work here. Waldo sadly passed away in July of this year, And we were privileged to have worked with him to take in his enthusiasm of life and everything else. Thank you.
Great presentation, Londi, and thank you very much for that great work. Are there any questions for Londi, colleagues? May I please have the roving mic? Where is it?
Thank you. Thank you for the great presentation and sharing your great innovation with us. You mentioned that the prototype, your product, performs better than the standard one that is available in the market. So I was just wondering, in terms of cost and accessibility, is it something that is going to be accessible to general population, or also compared to the available one, will it be expensive, or it can be accessible to the general population?
Okay. So the commercial one is quite pricey as well. It's not cheap. But this work, the next phases would be the commercialization of these implants, and with that, in producing many more, we trust then that the price of them would be not as expensive. I can't say it will be cheaper than the commercially produced one, but mostly we're looking to do impact with this work. And so a lot of pro bono work goes into it. The surgeon that we're working with, he works at a public hospital. So even the people that he's already put this prosthesis in, it was a state-funded surgery.
Any other questions? Okay. Okay, yes, sir. Yes.
Thank you very much, Londi, for the very inspiring work that you are doing with your team, and I want to emphasize the point that you make around impact, because at the end of the day, I think through your research, we'll be able to ensure that more people have access to this type of treatment, because it would be interesting for me to know, why are these things expensive? Is it just because, the whole issue of limiting access by artificially inflating prices of all the things that we have to buy? But the question I have is around, the fundamental reasons why the nickel-based materials perform better. Is it because of structural differences between the different materials, or maybe it's the next part of your research, because it will be interesting perhaps to understand that aspect as well, because maybe you can also, through that, design other materials which might even be cheaper, maybe not even metal-based, than the ones that you are working on now. And then the second point around the observation that the nickel-based materials perform better than the standard. If my understanding of that statement is correct, that you hear better, I wonder if that is a good thing, or maybe not such a good thing. Because maybe there are certain things that we are not meant to hear as humans.
Thank you for those questions, CEO. On the first one, my work is now cut out to really dive into, is it just the material properties of the nitinol or what else? In this experiment, the only difference was the material themselves. And so that's the next part of my research. And my PhD is actually on developing these nitinol materials for biomedical applications, because they also have a special shape memory effect, which in this application, for an instance, if you use it for the staples, the last part, you're able to then fasten onto either tendons or whatever it is on the ears without physical crimping and things like that. So I'll let you know once I am very certain on what it is exactly. On the second question concerning Now I'm blanking out. The better performance of the nitinol compared to the standard. So the standard prosthesis, or the standard measured sound transmission, is on the commercially available prosthesis. And so our aim is to look at, with these 3D printed prostheses, can they transmit sound firstly? And what we saw is, yes, they can transmit sound. If we had put in a silicon something, for an instance, as a material, silicon can't transmit sound. But in doing better than the standard, there's also the loudness part of sound hearing that we were talking about. So what this is that then you'll be able to hear a bit better with sound at these particular frequencies. It's the loudness where you probably don't want to hear very loud things. And this is not quite touching on that as yet. I hope I answered you.
Thank you, Londi. What I would like to find out is, can this material last a lifetime, or does it need to be changed maybe after a certain period of time?
These materials are biocompatible. So firstly, they're able to sit in our bodies without bringing harm to our bodies. And yes, they are durable. We do biocompatibility or cytotoxicity tests to validate the material's biocompatibility, to ensure that then it's safe for you and that it will last and it will not degrade while it is inside your body.
Oh, thank you very much. If we wish to interact more with Londi, can we catch her during the break so that we can save time? For now, can you please give her a big round of applause for the great work she's doing. Thank you so much, colleague, for that. Our next speaker will be Mlondi, who is an MSc candidate. May we please invite Mlondi, please come forward. Mlondi is going to be talking to us about advanced oxidation process for the degradation of chlorobenzene using TiO2 catalyst. I'm not sure what the full name is. Over to you, sir. So the talks are 15 minutes, and we've got 5 minutes of questions. So I will be timing you. And I welcome my colleague, Kelvin. Please come forward, sir.
I extend my greetings to all present today. My name is Mlondi Cili, and I'm a university student at the University of Zululand. And today I'll be presenting my study on the advanced oxidation process for degradation of chlorobenzene using titanium dioxide catalyst. It was under the supervision of Professor Pulabotla. So you may ask yourself, what is chlorobenzene? Well, chlorobenzene is a toxic, chemically stable, and oxidation-resistant chemical that is associated with various hazards such as skin irritation, eye irritation, irritation to the respiratory system. However, in severe cases of high exposure, it is known to cause damage to the liver, kidneys, and even the lungs. And in the worst case scenarios, it can even lead to death. As you can see from above, it poses potential pollution risks from the release of or improper disposal of chlorobenzene-containing pesticides, or the improper disposal of pharmaceuticals, plastics, dyes, or cleaning solvents containing chlorobenzene. While traditional attempts have been made to decompose the chemical, such as oxidation under activated charcoal, it has been found that a lot of studies have failed to decompose chlorobenzene completely, and also doing so, it has failed to decompose it into environmentally benign or environmentally friendly products. In worst cases, you find more toxic or more carcinogenic byproducts being formed such as your PCDFs and PCDDs. As I said, activated charcoal has been used in traditional methods. Other methods such as catalytic combustion have also been used. However, these methods use very expensive noble metal catalysts and very high reaction parameters, which are infeasible for large-scale application or practices. Therefore, the need of this study is to develop a method to decompose or degrade chlorobenzene completely, and in doing so also yield more environmentally benign or friendly products. It will also be advantageous if the process was able to be more financially feasible and easier to control. Therefore, in guiding this study, the following research questions were posed, such as, will the chosen process have sufficient control over reaction parameters throughout the reaction? What effect does the pH during the synthesis of the catalyst have on the outcome of the degradation? Would the catalyzed ozonation favor the production of environmentally friendly products? And finally, would the catalyzed ozonation be viable for large-scale approach? As I said, the study aimed to synthesize titanium dioxide via an adapted sol-gel technique, whereby the pH would be varied across the different mediums. So you'd have acidic medium, pH 3, neutral at 7, and basic at 11. Again, it will be applied for the ozonation reaction. Again, guiding the project, the above objectives are to be considered. Synthesis of titanium dioxide within the pH ranges, followed by characterization by FTIR, TEM, XRD, and calibration of ozonation generation, as well as application of the titanium dioxide in the ozonation reactions, followed by a study of the sample aliquots by GCMS to analyze the products that will be formed from the reactions. And therefore, a study will be made on the percentage conversion and product selectivity from the reaction. For my catalyst, I have decided to use titanium dioxide, not only for its non-toxicity, but also it has shown promising results in various oxidation reactions. Advanced oxidation processes. Advanced oxidation processes are oxidation processes that involve the generation of stronger oxidizing radicals or stronger oxidant species. In this case, I will be generating ozone, which has a high oxidation potential of 1.07 electron volts, which is far higher than the 1.23 electron volts seen in oxygen. Above, you can see how the possible degradation mechanism can occur, whereby the double bonds from the chlorobenzene can be attacked by the ozone molecule to form the ozonide intermediate species. For the adapted sol-gel technique, I have used titanium trichloride pentahydrate precursor that was diluted in ethanol and mixed with a solution of sodium hydroxide, which would be mixed in nitrogen conditions to control the temperature, as maybe you may be familiar with titanium chloride precursors. They tend to be very exothermic. So this was necessary to ensure that no damage would occur to the catalyst. And of course, pH would be continuously monitored during the entire process. Afterward, heating and agitation of the reaction solution would be done in order to bring about proper nucleation of the titanium dioxide. This would ensure that the synthesized material would not fall out of the 1 to 50 nanometer range for catalysts, which is considered the more optimum particle sizes for catalytic applications. Afterward, the solution was aged for several days, 5 days, in order to stabilize the catalyst. This would ensure that they were less prone to oxidative degradation themselves. Hence, the catalyst would also be able to be reused for further oxidation processes. Then afterward, drying and rinsing would follow, again with further drying and calcination. Above is the schematic of the ozonation reaction, which would be conducted in 24-hour periods, whereby the sample would be introduced into the impinger and the ozone would be bubbled into the reaction solution. Below are pictures of the synthesized titanium dioxide. XRD analysis revealed peaks at the 101, 004, and 200 planes, which is synonymous to the anitase phase of titanium dioxide, showing that the study was able to successfully synthesize titanium dioxide. However, closer inspection of the diffractograms would reveal that the pH 11 was only able to be distinguished in one of the frames. So, henceforth, it was deemed too amorphous for application in the study. Analysis of the FTIR spectrum would reveal broad peaks around the 3,000 to 3,700 region, which is resultant of the vibrational stretching of hydroxyl bonds. This is commonly seen from absorbed water within the crystal. Again, you can see more vibrational stretching due to the presence of absorbed H2O vibrational stretching, which is around the 1,500 region. TIM micrographs were also analyzed via ImageJ software and confirmed confirmed pH3 titanium dioxide to be present in average particle sizes of 8.21 nanometers and pH 7 synthesized titanium dioxide to have average particle sizes of 11.88 nanometers. Again, closer inspection of the particles you can see that there is irregularity in the structure of the titanium dioxide in both cases. You can see that the structure is not very crystalline, more rough, like irregular, no repeating patterns, which is kind of validates the analysis that was seen from the XRD and FTIR that water was absorbed by the crystal. Below is a chromatogram showing the elution of chlorobenzene blank sample. As you can see from the above, the ozonation of chlorobenzene in the absence of catalyst material achieved a degradation or decomposition of chlorobenzene at 50.57% with a selectivity of 41.59% to ethyl hexanoate. This was seen after the full 24-hour period. Ozonation under the presence of activated charcoal, which was done as a control, was seen to yield conversion of 83.12% after 12 hours. However, it had a lower product selectivity toward ethyl hexanoate, as you can see with the 38.02%. Then the pH 3 titanium dioxide was found to have a much lower yield of degradation, which was 38.90%. So in other words, it was found to inhibit the degradation of chlorobenzene, while it only had a 22.21% product selectivity to ethyl hexanoate. Then finally, under the pH 7 titanium dioxide, it was found that the highest conversion of 95.71% was observed after 12 hours, with an 18.23% selectivity towards ethyl hexanoate. To summarize the findings from these results, it was confirmed that titanium dioxide was successfully synthesized at the anatase phase by the various JC-PDS card number. The amorphousness of the structure was confirmed by the presence of absorbed water functional groups from the 3,400 to 3,700 region of the OH vibrational stretching and in the 1,600 region for the H2O vibrational stretching. 10 micrographs were successfully synthesized of the desired range. And thereafter, GC-MS results of the uncatalyzed ozonation reaction were used as a basis for comparison of the catalyzed reactions, whereby 50% was seen for the uncatalyzed reaction. In comparison to the activated charcoal, it had an increase in chlorobenzene degradation. However, with pH 3, we saw a decrease, or rather an inhibition of chlorobenzene degradation, while also the pH 7 was seen to increase the degradation of chlorobenzene with the highest conversion of 95.71. Of course, in conclusion, it can be said that while, because of the inability to apply the pH 11 catalyst, it's inconclusive to say or to conclude on the effects of pH on the catalyst performance for degrading chlorobenzene. However, since high degradation was observed in the pH 7 titanium dioxide, this can serve as a basis for further research and study for degradation of chlorobenzene. As well as you can see from all the reactions of the uncatalyzed activated charcoal and titanium dioxide, ethyl hexanoate was observed in each of the sample aliquots. Therefore, this serves to make a guide or a claim that ethyl hexanoate has the potential to be a major product from ozonation of chlorobenzene. However, due to a shortage of resources, the study was unable to actually proceed with the synthesis of more pH 11 titanium dioxide, hence why the study is inconclusive on the pH effects of the catalyst performance. Below are my references, and I would like to acknowledge my professor, Pulabotla, and my fellow seniors and colleagues within the catalysis research group of the university. I also wish to acknowledge the funding I received for my honor studies by the National Research Foundation. Thank you.
Thank you so much, Mlondi, for your talk. So now, before I open the floor for the audience to ask you questions, so Mlondi, pretend I'm your aunt who hasn't visited you for 3 years. And now I want to find out, hey, Mlondi, my nephew, I understand now you are at UniZulu, you are doing your master's. What exactly are you doing? What have you found out? And how do you think your project will change the lives of South Africans?
Well, if I can try to simplify it, I am decomposing a polyton. But in my doing so, I'm not only trying to decompose it, but I'm also trying to form products that will be beneficial for future use. Like, for example, ethyl hexanoate is an ester, so it can be used for aromatic purposes like fragrances and food purposes like like the same, yeah.
Okay. Thank you, Mlondi. Well done. Congratulations. Well done. Now the floor is open for you, colleagues. What questions do you have for Mlondi? Yes, sir.
Thank you very much, Mlondi, and congratulations on the very excellent work that you've done and very detailed characterization. And as you said, taking something which is a pollutant and making a potential flavonoid. That is really excellent work. The question I have is, as you know, titanium exists in two structural forms, anatase and rutile. Did you consider using rutile also as an option?
Oh, yes.
For this catalytic process?
Yes, I'm aware that titanium dioxide is present or found in three various phases, being bruchite, anatase, and rutile. However, I opted not to use rutile because of its thermodynamic stability. Because for future studies and applications, I wanted to make full advantage of the photoactivity of the anatase phase.
Thank you, Mlondi. Any other questions, colleagues? Okay, thank you so much. Okay, please, sir.
Good morning, and thank you for such a beautiful presentation. I just have a question with regards to your synthesis of your catalyst. What was the specific of you using ethanol in your synthetic process for your soldier?
Oh, I use ethanol as a means to dilute the precursor, because you find with soldier technique, you have to kind of reach for a certain pH. So in your reaction solution, you have to first put in your first solution, which is acidic, then introduce or inject your basic solution. However, doing so without diluting the acidic one may make reaching your desired pH more difficult. So diluting the acid is easier to control the pH.
Okay, thank you.
Thank you. We've got another question here.
Thank you for the talk. I just have a simple question. It's more from a point of ignorance. But does your process of generating your titanium oxide affect the size of your particles? I saw you had a TEM and you had a range of sizes. And would those sizes affect the degradation of your chlorobenzene?
Yes, of course. As often you would find, the sizes of your particles is very important because it affects the surface chemistry of the catalyst. And oftentimes you find that particles that are smaller tend to be more prone to damage, while particles that are far too big don't have that efficient oxidation capability. So now, if you try to control the size of the catalyst to be within a range of 1 to 50 nanometers, it usually yields more consistent results.
Thank you, Mlondi. Well done, Buti, and all the best with your studies. Can we please give him a round of applause? We are now going to invite our next speaker, that is Mashwale Mamabulu. Please come forward, Mashwale Mamabulu. Mashwale is going to present to us investigating the structural properties of monoclinical crystal structures. Thank you. Thank you. Over to you, sir.
Good morning, everyone. I go by the name of Mamabolo Mashawale Stuart. I'm from University of Limpopo. I just joined the energy storage, which the CEO just mentioned. Or there's a center at the University of Limpopo where we are working on batteries. So I'm one of them. I just joined them recently. I'm new. So I'm going to give a talk titled Investigating the Property of a Monoclinic Crystal Structure, a lithium aluminum pyrophosphate solid electrolyte material. The study is under the supervision of Dr. D. Tlongwane, Dr. K.T. Malaji, Professor P. Ingwebe, and Professor R.S. Ledwaba. So, as the population grows daily, also the activity grows daily. We all know that we spend more time on our electronic devices, we travel using cars, then we also use some appliances at home that need energy. So lithium-ion batteries have been used for over 3 decades now as to power a wide range of applications such as electronic devices, our phones, laptops, cameras, and etc. So, and electric vehicles also as a large smart grid. However, these lithium-ion batteries were using a liquid electrolyte, which poses challenges such as short life cycles, safety issues such as explosion, leakage, and flammability. Also, thermal and electrochemical instability and low energy density. So, however, recently solid electrolyte have been introduced to address the issues experienced by liquid electrolyte. We can sometimes, when you are driving at some road, you see a car burning because their batteries can explode. They are using liquid electrolyte, which form some reactions during when the heat is subjected. Remember, an engine of a car can heat. So you can sometimes, when driving on the road, N1 or wherever, you see that we see a car burning. Liquid electrolyte batteries are one of the issues. So to address this limitation, we came up with 3 materials, of which this one is very new again. Have never been explored as a solid electrolyte, so I'm trying something new. Yes. So, a lithium aluminum pyrophosphate, which is a Nasicon type structure. So we are studying this material as a solid electrolyte since it has a potential to deliver high lithium ion mobilities and through its dimensional framework resulting in high ionic conductivities and improved battery performance. So in this study that I'm presenting, we haven't calculated the ionic conductivity since the material is still new and has never been reported in the context of solid electrolyte. So however, the structural properties of our material are not fully explored, especially its electronic properties, which is a critical performance matrix for solid electrolyte. So in this study, we are using DFT, density functional theory, to investigate the properties of these materials. So here is our structure. I'm not sure. Can I also do it? Here is our structure, which have a 3D framework where this structure is phosphate, which is attached to 4 oxygen, and aluminum, which is attached to 6 oxygen. These 2 groups, the octahedral and the tetrahedral, share oxygen corner to form this 3D framework. We calculated the lattice parameter of this. This material has the following lattice parameters. So, like I mentioned, this solid electrolyte batteries can be used in laptops, cell phone, cameras, and so forth. Also in electric vehicles and smart grid. So in this study, for all density functional theory calculation, we used a VASP with a projector augmented with pseudo potential, which this projector with augmented with pseudo potential. We are using it, taking advantage of it giving us accuracy, predicting accurate results. So we also use a GGAPBE as our exchange correlation function to optimize this structure. So we used the automated convergence where our cut-off energy were found to be 553.928 electron volts, and our K point were found to be 5 by 3 by 4. So the fully converged structures, when I say the fully converged structures, I mean now we have optimized our structure. Now to allow the volume, the cell shape to relax. Like to relax and change. So the fully optimized structure, we are now used to calculate mechanical properties, structural and electronic properties. Remember I said the material have never been explored in the context of solid electrolyte, but it has been studied before. So we calculated the lattice parameter, our A, B, and C with PBE sol, and compare it with experimental reported by Shogo and co-workers. So our A parameters, you can see from our plot here, our values are not far from each other. So since we can just conclude already they are close to each other, we calculated the percentage difference of the lattice parameter, and they are all under 3%. So this means we have successfully reproduced the structure. So we further calculated for a good solid electrolyte, it must be mechanically stable. So we calculated the elastic constant, where the elastic constant is the physical property that describe how material respond to the stress. When you apply a stress to the material, what happened to the material? So our material is a direction-dependent material. So we calculated the elastic constant with the CIJ, and we got the following elastic constant. So, however, there is a bond stability criteria for monoclinic system. So, for a monoclinic system to be mechanically stable, it must satisfy the following criteria, bond stability criterion, of which our material have certified it. So, this elastic constant for applications, it helps us in, like, remember you're working on a structure, a solid electrolyte where we have the A and B and the C. So we want to know what happened in the A direction. Does the A direction change whenever the stress is applied? Is our material stiff in the A direction, B direction, and C direction? So this elastic constant helps us to check if our material are really stiff and in both the direction. So we also calculated the elastic modulus, of which is also the mechanical properties. So we have the bulk, the shear, the Young and longitudinal. So for all these values must be greater than 8.65 gigapascals for our material to be mechanically stable. And again, we have a bulk, of which bulk measure the material, this bulk measure the material compression. Will our material compressed when a force is applied to it or a stress? So getting 41.97, this means our material can, which is very far from 8, our material cannot compress. This means our material is stiff, which is good for a solid electrolyte. Here also measure will our material stretch, which is also good since it's far from 8. Our material cannot stretch under applied force on it. We also have Young's and longitudinal modulars, which also tell us about, will our material deform, will our material break, is our material stiff? But with our value here, our material is stiff and cannot deform under applied stress of external forces. So to check if our material are brittle or ductile, we use the post ratio. Then we got a post ratio of 1.08, and if you check the condition there, if the post ratio is less than 1.75, this means our material is brittle, otherwise ductile. So together with the Poisson ratio, which tells us our material has to be, for a metal to be brittle, it must be less than 0.26. We also calculated the Cauchy pressure, where if you get a negative Cauchy pressure, this means our material is brittle. So our material satisfies all the conditions to check the brittleness. So our material is brittle, of which means our material is subjected to cracking and fracture. So the bulk and the shear in a battery, it helps us to suppress the formation of dendrites, of which can cause a short circuit in a battery, which leads to safety issues. So our material, this material resists the formation of the growth of the dendrites. And again, in also the electrolytes I've read from the literature, they are all brittle. So to address the issue of brittle in this material, in order for a material not to crack or fracture, we will use various dopant to dope our material. So, but our material, since with the post ratio we have 1.08, it means our material is less brittle. So here we calculated the band structure to check a good solid electrolyte must be an insulator so that it suppresses the electronic conductivity. We don't want electronic conductivity. We don't want to conduct electricity here, but we want the lithium conductivity so that we will get a high ionic conductivity. So we found our material with a wide band gap, which means our material is an insulator. Also, the density of state proved that our material is an insulator, with showing the gap there, that this material is an insulator. This density of state and band structure gave us the same result. This means what we are doing, we are in a good direction. Yeah, we are in a good direction. So we further calculated the energy of formation to check if our material is thermodynamically stable. So we find our material to be thermodynamically stable with the energy of formation of 269.28 kilojoules per mole. This means for our material to form, this energy was released to the surrounding in order for our material to form. And this means our material cannot break into its constituent element. So our metal is thermodynamically stable. So we're good to go and to continue with the solid electrolyte. We are not stopping. So in this study, the structural, electronic, and thermodynamic property of our metal were investigated using DFT and BBE salt exchange correlation function. The material demonstrated a mechanical and thermodynamic stability confirmed by the formation energy and elastic constant. The calculated wide band suggested that our material is an insulator for suppressing electronic conductivity. The poison ratio and caoutchouc pressure suggested that our material is brittle but is stiff and strong enough to resist elastic deformation. Here are my reference. I would like to thank the following party, the CSIR, for financial support and allowing me to present my work here, the University of Limpopo for allowing me to register, the Material Modeling Center for academic, they give me supervisor this center, and then the HPC for computational resources. And I thank you.
Thank you, Mashawale, for the wonderful and entertaining talk. Maybe before I throw the questions to the floor, I just had one simple question. For your structural properties, you showed that for your model and for the experiment, they were kind of similar. I was wondering what's the error that you would, what's the error margin that would maybe make sense in terms of, is there an error margin where the values are no longer aligned?
Oh, thank you for the question. Basically, in this study, we are using 3 different functional. So with the functional that I use, the PBE sol as an exchange correlation function, is the one that gives us the best in terms of combination, comparison between the experimental lattice parameter and ours. So it's the one that gave us the closest.
GGA that, okay.
Yes.
Thank you. I'll open the, okay. Please go ahead.
Thank you for the delightful presentation. Maybe I missed something, but you concluded that your material is mechanically stable, but then you mentioned the brittleness that might cause cracking. So, yeah, like I cannot link the two.
Okay, thank you. Oh, like I've mentioned that for also lead electrolyte that I've came across, we expected it to be brittle, but it is less brittle. So, yeah, it is less brittle. But for future work, we are going to introduce dopant into a material, at least to direct it to be a ductile. We are also going to derive potential that will help us at least become with a post ratio close to 7.5, which will be half brittle, half ductile.
Do you have like an idea of the measures that you'll take to reduce the brittleness?
Yes. So like we are going to dope our material with a heterovalent dopant. So yeah,
okay.
Of which you do. Yes.
Thanks.
Thank you. Are there any further questions? Yes, please.
Hi, thank you for your presentation. My question is then, with your dopant, do you know then its effect on your other properties, your thermodynamic stabilities and other things?
Yeah, thank you very much for the important question. Basically, the question is very important, but basically we are using a high throughput method to screen a large number of dopants. So we are going to identify a dopant that will not compromise other properties like the other stabilities. So the high throughput will help us identify that a dopant that will not affect other stabilities. Like, yes, thank you.
Sorry, colleagues, because of time, I think maybe we should just jump to the next speaker. I'd like to thank the speaker, Marshall. Thank you for the wonderful talk. So our next speaker is Jacqueline Tao, and she's going to talk about high entropy alloys for hydrogen storage. Please welcome the next speaker.
Good morning, ladies and gentlemen. Yesterday, there was something that was lifting some of us who are short here. So, okay. Morning, ladies and gentlemen. As I've been introduced, I'm Tao Jacqueline, a master's candidate at the University of Pretoria, under the supervision of Dr. Mudiba, Dr. Mate, and Prof. Bejana from CSIR, and Prof. CSIR from the University of Pretoria. And my talk today is on high entropy alloys for hydrogen storage. Now, with the world's rising energy demand driven by the economic and the population growth, which happen to put a strain on the fossil fuel-based technologies. And however, those fossil fuels are the major contributors to the climate change and also the greenhouse gas emission. So to mitigate all these challenges, this has pushed the research community to now focus on the low carbon energy alternative solution, whereby, yes. So, as I was saying, this has now pushed the scientific community to now look into the low carbon energy alternative solution, whereby hydrogen has emerged as one of the possible replacement for fossil fuel, mainly because of its high energy density and its environmentally friendly in nature. But despite all those advantages of hydrogen, the lack of the safe and efficient hydrogen storage techniques with high volumetric and gravimetric capacities limits the adoption of the hydrogen-based technologies. And currently, hydrogen is stored in high pressurized cylindrical tanks and also in cryogenic temperatures in liquid form. And on the other side is also stored in solid-state materials. And these solid-state materials include your MOF materials, your metal hydride, and hence the development of the high entropy alloys for hydrogen storage. Now, these high entropy alloys are another class of the metal hydride group. So they are the type of alloy material that is made up of at least 5 or more principal elements in equal or near equal atomic compositions, ranging between the chemical composition of about 5 to 35 atomic percent. Now, they are known to form single crystal structures, such as your BCC, your FCC, and the hexagonally pegged structure. And due to their excellent mechanical and functional properties, such as your high strength, good structural stability, good resistance to wear, corrosion and resistant, they've been used in many energy storage applications, and including the hydrogen storage. And there are different techniques that have been employed to produce these high entropy alloys, which includes your arc melting, your ball milling, and also lately additive manufacturing, whereby the directed energy deposition is also explored. And in this project, we used, or the focus is on the directed energy deposition. Now, hydrogen can be stored safely and efficiently in solid-state material in high volumetric and gravimetric capacities under ambient conditions. And amongst the different solid-state materials, our focus is on the metal hydride, mainly due to its ability to operate under moderate pressures and also to store hydrogen in high volumetric capacity. And however, according to the US Department of Energy, for us to consider these high entropy alloys as the potential hydrogen storage materials, they must at least be able to achieve high gravimetric capacities of at least 4.5 weight%, with an ultimate goal of reaching the 7 weight% that we see on the graph. Now, with what is currently happening in the research community, the BCC structured high entropy alloys in particular have gained significant attention in the hydrogen storage, mainly due to their loosely packed structure, whereby they may provide more available interstitial sites whereby our hydrogen can be stored. However, given that, there is still a need in terms of achieving the high storage capacity. And while the BCC have shown superior hydrogen storage capacities, the Lave phase they've also demonstrated the reversible performance at also room temperature. So ideally, we want to develop energy storage material that can operate under ambient conditions for safety purposes. So, and previous studies have shown that using these elements, you can achieve those BCC and the Lave structure, and also they are also regarded as the promising candidate for our hydrogen storage material. And the high entropy alloy with the highest storage capacity by far was reported by Chen with the highest storage capacity of about 3.7 weight%, which is still far beyond meeting the target set by the US Department of Energy. So therefore, there's still a room for us to improve on that. Now, the aim of this study, looking at the costs, is to use the computational modeling and simulation to investigate the hydrogen storage properties and the desired phase of these high entropy alloys for hydrogen storage capability. And the objectives, we are going to look at the hydrogen storage properties and also investigate the phase desired. And once we're done with that, we'll then move into now experimentally fabricating those simulated high entropy alloys using our in-house DED additive manufacturing system. As I said, we are going to look into, we are going to use the computational modeling. In the field of modeling, our work is to develop those models and then we validate them. So one of our scientists developed this PCT curve model to evaluate the applicability of our material for hydrogen storage. Now, the ability of these materials to store and release hydrogen is highly dependent on their pressure composition temperature curves, which predicts the absorption and the desorption capacity of the material. And eventually we can analyze the storage capacity of our material. And that operates under this principle on this figure 5 here, whereby initially you will have your sample. In our case, it will be the printed sample in metal form, and then you degas it with hydrogen. So you introduce hydrogen atoms on the material, and then as it gets absorbed, we get to form an alpha phase there. So, and as the hydrogen content now increase with the increasing pressure, we then get to see those increase in hydrogen content, and also with the increasing pressure. And as the material gets to absorb more and more hydrogen, now we get to see the two phases now, which is now the material and the hydrogen being absorbed within the interstitial sites. And once those two phases now start to coexist together, we see a flat plateau region there, whereby the area under this plateau curve tells us about the capacity of the material to store the hydrogen. And now we no longer have the metal and the hydrogen, but now we have a metal hydride in that beta phase. And at that constant temperature and pressure, we are able to also obtain the Van der Hoef plot, which tells us, which gives us other thermodynamic properties of our material during hydrogenation, whereby each of those properties tells us about the stability of the material and also how well did the material bond with the hydrogens. We then moved further to use another technique now to analyze the phase formed. Now that we have established the capacity of the material to store the hydrogen, we now look into the phase formation. We then used this software here, the high entropy alloy prediction software, which uses your chemical composition of your alloy to calculate these semi-empirical parameters, which are your entropy of mixing, enthalpy of mixing, your atomic size difference. Mind you, you are mixing different elements with different atomic sizes. And all that, they will be able to evaluate your the phase formed in your material. Now, using that Python code, we were able to now evaluate the storage capacity of our material, looking at these two alloys. And the composition of these alloys were influenced by the literature that I mentioned before, that the likes of titanium, vanadium, and chromium, they have got high hydrogen affinity. Therefore, they give you a chance of obtaining higher storage capacities. So these two alloys were both evaluated at room temperature and also at 100 degrees, and we were able to obtain storage capacities of about 3.8 weight percent and also 4 weight percent. So the 4 weight percent is at least promising regarding the target set by the US Department of Energy. Now, with our phase formation, we then calculated these semi-empirical parameters, And according to literature, it has been reported that the likelihood of forming a BCC structure increases as the VEC value is below 6.87, and that chance decreases as you go beyond 8. However, other researchers have also discovered that not only the VEC can tell us about the phase formed, but also the atomic size as well contributes to the phase formation. And it was discovered that the other phase that I mentioned earlier on, which is the Larvae phase, happens to occur when the atomic size difference is greater than 5%, and another parameter, which is the alliance electronegativity, which is greater than 7%. Okay, sorry. So based on our results, we can tell that although we are forming a BCC based on the VEC number, but there's a possibility of us also forming the Larvae phase. Now, in our high entropy alloys, we are using elemental powders. So we're mixing all those powders, and what you see here is the powder mixing process. And after mixing, we then take them to our DED system in order to be able to print our samples. And what you see here is the printed samples on a titanium base plate. Now, after mixing, you need to check the ratios of, or the chemical composition of your powder before even going to print, right? So what you see here, it's the mixture of those elements that we see here. So we do a SCM analysis through EDS to obtain the elemental composition of our powder in order to check the homogeneity of our powder before printing. And what you see here is the chemical composition obtained through the EDS. This is after mixing, and we can see the chromium content happens to be higher than the other compositions, and this mainly can be due to the inhomogeneity. The inhomogeneity is influenced by the particle sizes of your powder matters, and also the densities. So you may find that your elemental powders, maybe they are not all spherical. That plays a huge role into your powder mixing. However, after printing, we then observe now the chromium content has now reduced, and then we see an increase in the titanium composition, and this can be due to the diffusion of that. Remember, we printed our samples on a titanium base plate, so this can be due to the diffusion of the titanium into now the material. And what we observe on figure 9 there, figure 9A, we have the morphology of our material. So after printing, we then go and cut the sample, and then we analyze it. We look at the morphology, we call it the microstructure of the material. And what you see there, it's what we call the dendritic microstructure, with the darker regions rich in titanium content, and the gray regions rich in vanadium and chromium. So the darker region, this simply means that during the DED process, the titanium segregated into these darker regions. Now, like I said, we do the modeling, and then we move into experiment in order to validate our simulations. we were then able to now validate our phase formation. And what you see here, it's the actual composition that we had initially with those semi-empirical parameters. And then this is after mixing the powders. We're observing if the VEC number, is it still within the formation of a BCC structure? And by looking at these values from the actual composition into mixing and the DED printed samples, we can see that we are all, we are obtaining a BCC structure throughout. And then we went on to now do even XRD to validate the predictions. And then from our XRD data, we can see that indeed we are forming a BCC structure and that possible Lavey phase structure. Now, in conclusion, I can confidently say that the two high entropy alloys were successfully investigated, which demonstrated excellent hydrogen storage performance by absorbing large amount of hydrogen with storage capacities of about 3.8 and 4 weight% at those temperatures, 25 and 100 degrees respectively. And the criteria used for phase prediction indicated the possible formation of a single a single BCC phase structure, and with the VEC number of less or equal to 5.4. However, the XRD also revealed the presence of the Lavey phase structure. Now, in overall, these results demonstrated that the phase combination demonstrate a balanced hydrogen storage method that enables the alloy to absorb significant amount of hydrogen while maintaining its stability over time through those PCT curves that we observed. Now, for future work, I don't know, future, it can even be tomorrow, right? Yeah, so with the future work, looking at these results that we have, these are theoretically based. Therefore, we still need to perform hydrogenation in order to confirm those storage to confirm those storage capacities to validate our simulations. So, as I said, future can be tomorrow. This is currently underway. We're hoping by the end of September, we'll have the hydrogenation results in order to validate our simulations. And what I can say also is that this work was also published at Rabdasa. So if maybe you need more clarity or have more in-depth of what is going on, you can find my paper online. I think even on ResearchGate is there. And I would like to acknowledge the following parties: the University of Pretoria, Department of Science and Technology, and the CSIR for their support, and also my supervisors. I thank you.
Thank you, Jacqueline. Thank you for the wonderful talk. Before I open the questions to the floor, I just had one quick one. I saw you produced alloy 1, but alloy 2, you didn't produce it. Is it because, is there a specific reason why you didn't?
At the time...
Oh, sorry, you didn't hear the question. The question was, I saw she produced alloy 1 experimentally, but she didn't produce alloy 2, so I was just wondering why alloy 2 wasn't produced.
Yeah, so During the time this work was supposed to be submitted for Abdasa, I had only produced Alloy 1. But now I've recently produced Alloy 2. So it was mainly due to resources at the time. Yeah.
Oh, okay, thank you. That's wonderful. I'll open the questions to the floor. Are there any questions? Yes, please.
Thanks, man. Great presentation. I wish I took the actually registered this based on this topic. I once had an offer to do that, but my question is simple. I wanna check with your material. Did you look into it specifically for the mobile or the stationary storage? Because I'm looking at if it's in for mobile, there is a kinetic movement within. So is that not going to affect the material implementation of your actual implementation of your material? Thank you.
Can you repeat the question?
Okay. I'm asking, based on, should I say, your simulation, and looking in terms of the storing of your hydrogen, then my question is based on, you were looking on the storing specifically on the stationary phase or in the mobile phase? In the mobile phase, I'm meaning in terms of the transportation. So now I'm looking at, is that not going to affect the way you assemble your storing aspect of it?
Yeah, hey, that's quite interesting. I can say, yeah, no.
Sorry, but it's fine. We can consider it in terms of looking into it.
Yeah, maybe moving forward.
Thank you so much.
Yes, thank you.
Thank you. Yes, please.
Thank you for the presentation. I'm assuming you are basing your synthesis or design on the performance of that is related to the your conclusion. You said the maximum capacity yield you gave 3.8 and 4%. So how does it compare to the other technologies that you've mentioned?
You mean the likes of MOVs?
Yeah, the storage hydrogen
materials.
Storage, yeah.
So the other materials, some, although they can store as much, but the problem is the operating temperature and pressures. So some you find that they are operating at high pressure, but then when it comes to the kinetics of the materials, it's not performing very well in terms of releasing and absorption of the material, although it can store that much. So hence I said, in our case, ideally we want to operate within the ambient conditions. And also that is also guided by the target set by the US Department of Energy. They want, those are specific storage capacity that they are saying we must achieve. They've also put those operating conditions there as well.
Okay.
Yes.
Thank you for the question. Go ahead, Daryl.
Hi, Jacqueline. Yeah, thanks for a good talk. My question's not actually a question. It's more that I popped into the CSIR newsletter, and I think we'd like to wish you a happy birthday for today.
Thank you. Now my day is made.
Yes.
No, I just wanted to ask, what does the South African standard say in terms of that storage? Because you referred to the US one.
Hey, the South Africa. I think you're raising a very good point there. Yeah, maybe that's something that I'd also need to look at within where I am, not like base whatever that I'm doing on what the world at large is. Yeah.
Thank you.
Thanks.
Okay. I think we have a question again.
No, I wanted to help her in terms of responding to him, but there is no standard specifically for South Africa because we depended mostly on the standard, specifically on the hydrogen. I attended, I think it was more of the policy and standard development. So it's where they're still looking in terms of the way of aligning within the standard that are already existing. Thank you.
Thanks, my brother.
Colleagues, we have a few minutes, not to do it on your birthday, but we have a few minutes for one or two questions. Thank you, Jacqueline. Thank you for the wonderful talk. Our next speaker is Ronewa Padagi. Please welcome the speaker. This topic is modification and application of PES UF membranes using ion MOF and ion MOF at GO. Okay.
Good morning, everyone. My name is Ronewa Padagis. I have been introduced. I'm a PhD student at UNISA under the Institute of Nanotechnology and Water Sustainability. My supervisors is Professor Mtlwadi and Dr. Madziva. Today I'll be giving a talk titled Modification and Application of Polyether sulfone ultrafiltration membranes using ion-based MOF and its composite with graphene oxide. Basically, in this project, I was looking at enhancing the hydrophilicity of ultrafiltration membranes so that they can be used industrially because the current membranes, they are hydrophobic, which limits their applicability industrially. Like I said, from my application of my work is using membranes with a application in water treatment. So in this way, we'll be looking at leachate treatment, but basically we can use the membranes in treating all types of wastewater. So we'll be looking at leachate because it consists of organic matter, inorganic salts, organic trace pollutants, and heavy metals, which makes it hazardous. It ends up contaminating surface water and underground water. So to prevent this from happening, there's a regulation in South Africa which says that every landfill needs to have a leachate management system. So different landfills treat leachate differently. The most common method is Fenton process and reverse osmosis. The problem with Fenton process is that it produces a high amount of ion sludge, which creates problem in disposing it, and reverse osmosis suffers mainly from membrane fouling. A membrane fouling of reverse osmosis occurs in 4 stages. We have complete pore blockage, standard pore blockage, intermediate pore blockage, and cake layer filtration blockage. So to mitigate membrane fouling of reverse osmosis, we can introduce a polymer grafting, which is by introducing the hydrophilic monomers, which will increase the hydrophilicity of the membrane and thereby lowering the anti-fouling properties of the membrane. Or we can incorporate nanoparticles such as metal oxides and MOFs by blending method. And then after, we can also use pre-treatment of using microfiltration, ultrafiltration, coagulation, or flocculation process. But the problem with coagulation and flocculation, it requires additional chemicals, and these additional chemicals increase the overall cost of the wastewater treatment, and it is not in line with environmental sustainability. So in my project, we are proposing to use ultrafiltration membranes by pre-treating the leachate. We incorporate ultrafiltration membranes, and then from there we use the effluent we introduce it to reverse osmosis, and then from there the water can be reused or they can be consumed. The desired polymers to fabricate ultrafiltration membranes include polyether sulfone, PSF, PVDF, and PTFE. These polymers, they have good mechanical and chemical stability, but the problem is that they are hydrophobic, which means their applicability in water treatment. So to improve this, their hydrophilicity so that they can be further used in water treatment, we can incorporate nanoparticles such as metal oxides using blending method, or we can do polymer grafting. But the problem with polymer grafting, it compromises the mechanical stability of the polymer, which reduces the mechanical and chemical stability of it. And therefore, they cannot be used in complicated wastewater. So for blending method, it does not compromise the mechanical and chemical stability of the membranes. And then in this project, we are proposing to use blending method using MOFs, because MOFs have high surface area, they have high porosity, high tenability, and high durability. So these MOFs have been used in different fields of scientific fields, but the problem, they have poor hydrothermal stability, and they are produced from prolonged reactions, which leads to poor yield. So in this way, we aim to overcome these disadvantages by creating a composite with graphene oxide, and then we create a MOF composite with graphene oxide. The aim of my work is to introduce hydrophilic functional groups into polyether sulfone matrix, which will increase the antifouling properties of the resultant membranes. And then the hypothesis is that the incorporation of nanofillers at varying concentration will enhance the overall membrane properties up to an optimal loading. Thereafter, the nanoparticles will start to aggregate and lead to reduced membrane properties due to membrane defects. So it is important for us to investigate different concentrations of the nanoparticles so that we don't have membrane defects, because at the end we want to have membranes with better properties, unlike membranes with a reduced water flux. And then from there we synthesized the nanoparticles, which were MOFs. It was synthesized using one-part hydrothermal synthesis, where we mixed the metal center and a carboxylate ligand. And then from there, we subjected to hydrothermal synthesis. After 24 hours, it was centrifuged and washed, and then dried in an oven. And then for the composite with graphene oxide, it was synthesized the same way as the MOF, but in this way, graphene oxide was added into the solution and used as a template. And then membranes were fabricated using phase inversion method, whereby the casting solution consisted of PES, PVP, MOF, and also the composite of MOF with graphene oxide, and the solvent which was used was NMP. In this case, you can see that the PES, it was kept constant, and PVP was used as a porogen, which was responsible for forming the porosity of the membranes, and the nanofiller, it was increased because this was the properties which we're trying to investigate to see which concentration of the nanofiller will have the best water flux and antifouling properties of the membranes. When we increase the nanofiller concentration, the concentration of the solvent decreases. After preparing the homogeneous casting solution, then the solution was cast on a glass plate, and then it was immersed in water. After a few minutes, the membrane formed. And then from there, we characterized the nanoparticles using CSIR, TGA, and XRD, with FTIR for the graphene oxide, we see that it has 3 clusters. The first cluster is hydroxyl group. It has hydroxyl group. The second cluster is carbonyl group, and then it has alkoxy and epoxy group. And then for the MOF, we have 3 clusters, which is carbonyl group, which also consists of CH group. Then we have 2 types of carbonyl group, which is carbon double bond oxygen and carbon single bond oxygen. And then we have metal oxo bond, which successfully confirms that we have a MOF. And then we also have this these other absorbents for the carbon-carbon bonds. And then for the composite, we have the 4 clusters, which is for hydroxyl group from the graphene oxide and the MOF. And then we have 2 types of carbonyl groups, and then we have alkoxy epoxy group from the graphene oxide. Then we have metal oxo bond from the MOF. And then from there, we investigated the thermal decomposition of the materials, and then turned out graphene oxide decomposed in 3 stages, which was loss of moisture, and then from there we have oxidation paralysis of the framework. And then for the MOF and the graphene oxide, it decomposed in 3 stages. The first stage was loss of moisture, which was absorbed in the framework, and also water, which was coordinating within the framework. And then from there, we have decomposition of the oxygenated functional groups, which left forming carbon dioxide. And then from there, we have oxidation paralysis of the framework, leaving behind stable ion oxides. And then for the XRD, the GO, it has 2 peaks, and then this peaks shows that there was oxygenated functional groups which prevent the staking of the graphene sheet layers. And then for the MOF, we have 2 peaks, with the sharp peak and the broad peak. The sharp peak shows that there's a periodic crystallinity of the framework of the MOF. And then for the broad peak, it shows that the MOF which we created was in layered format. And then for the composite of MOF and graphene oxide, it consists of peaks from the graphene oxide and the MOF. However, for the graphene oxide in the composite is shifted into low intensity, which shows the encapsulation of the MOF on top of the graphene oxide. And also the oxygenated functional groups of the graphene oxide acted as a stabilizer for the MOFs, thereby creating a more crystalline material which had short wave and long wave range. And then from there, we did ACM and HR term. The ACM of the graphene oxide, it shows that it is made out of layers with nanochannels. And then for the ACM for the MOF shows that it is made of ultra-thin layers which fused together, forming a block-like shape. And then for the composite, it is made out of graphene oxide layers, sheets, as well as the blocks of MOFs. It is possible that this MOF grew on the oxygenated functional groups of the graphene oxide. And then for the term, the graphene oxide, it is made of transparent layers, transparent sheets, which are even visible on a carbon support. And then for the MOF, it is made of mixture of truncated and hexagonal motifs. It formed hexagonal motifs because they used the carboxylate ligand. It reacts with iron to form hexagonal motifs. And then for the composite of MOF and graphene oxide, it shows that there was anisotropic growth of the MOF on top of the graphene oxide. And then from there, we characterize the fabricated membranes. For the pristine membrane, it shows that we have CH group, we have carbonyl group, we have sulfonyl group, and then we have carbon-carbon bond groups. And then for the composite membrane, it shows the fingerprint of the PES, because PES, it was the major component in the casting solution. But however, for the composite membranes, we have a new bond, carbonyl bond, which is from the graphene oxide as well as the MOF, which shows the successful blending of these 2 materials. And then from there, we investigated the membranes using the ACM. We did the top surface, the cross-sectional, and the bottom surfaces of the membranes. The top surfaces of the membranes, they are all made of upper porous dense layers. But when you increase the nanofiller concentrations, the pore distribution changed, increased slightly. due to slow solvent, non-solvent demixing rate. And then for the cross-sectional membranes, it shows that it is made of upper dense layer with finger-like post structures. And then for the bottom layers of the membranes, it is microporous. These bottom layers, it saves no pupils infiltration. However, it acts as a support layer for the top surfaces. It can be seen that as you increase the nanofiller concentration, the porosity of the membranes decreased. And then from there, we investigated the fabricated membranes using AFM. AFM serves as a tool to support ACM images. It only gives information on the surface smoothness or roughness of the fabricated membranes. The rougher the membrane, the more likely it is to suffer from the fouling, and the smoother it is, the better it is from fouling. So you can see that the pristine membrane, it is more rougher, which shows that it is more likely to suffer from fouling, which is not good from what we were looking for. We want the membrane which is smoother, which is less likely to suffer from fouling. And then the valleys shows that it can easily trap the foulants, but it is smoother. Therefore, it can trap the foulants, but it can have a higher rate of fouling. It can have a higher rate of fouling and then also have a higher rate of pure water flux. And we want to have the membrane with higher pure water flux and less fouling. So, and then from there, we investigated the water contact angle and the pure water flux of the fabricated membranes. In this case, it is important to note that the membranes with the highest water contact angle shows that it is hydrophobic. Therefore, it results in the lowest pure water flux. And then as you increase the nanofiller concentrations, the water contact angle decreases, which shows that the membrane it is more hydrophilic. This shows that the membrane, when it becomes more hydrophilic, the water flux increases, which is what we are looking for, because the current membranes which are currently available commercially, they have low pure water flux because most of them, they are hydrophobic. So this is good because we want to improve the hydrophilicity of our membranes. And then from there, we investigated the water uptake, thickness, porosity, and rejection of the fabricated membranes. The water uptake from when we increased the nanoparticles, it also increased due to the hydrophilicity of the membrane was increasing. And then this year, we can see that the M5 and M6, the M6, it has low water uptake because it only consisted of a pristine morph, whereas for the M5, it consists of the composite of graphene oxide and the morph, which shows that which has additional hydrophilic functional groups which increase the overall properties of the membrane. And then from there, we investigated the thickness of the membranes. It shows that as you increase the nanofiller concentration, the thickness increased due to the increase in viscosity of the dope solution. And then the porosity also increased due to due to delayed solvent, non-solvent demixing rate. And then from there, we did mean pore radius, which increased, the pore sizes increased, and the rejection of the bovine ceramine albumin protein also increased due to hydrophilicity of the membranes because the BSA has both hydrophobic and hydrophilic regions. And then from there, we investigated the fabricated membranes to investigate the reusability, potential permeability, and total ratio fouling of the fabricated membranes. As you can see, this simply shows the results of the first cycle here. From there, to prepare the membranes, we compact it for 30 minutes using DI water to open up the macro voids, and then from there we subject it to filtration of BSA solution as a model foulant, and then we can see that the composite membrane, they lost flux to around 50%, and then for the pristine membrane, which is hydrophobic, it lost flux to around 30%. As you can see, it has the lowest water flux. And then from there, after backwashing with deionized water, the water flux of the fabric of the composite membranes which was regained was more than 80%, whereas for the pristine membranes, it was around 40%, which shows that the composite, the newly fabricated composite membranes, they have better anti-fouling properties, which is what we're looking for. And the total the cleanability of the membranes, it shows that the more hydrophobic the membranes, it suffers from irreversible fouling, and then for the hydrophilic membranes, it most likely to suffer from reversible fouling. This shows that the membranes which suffers mostly from reversible fouling, they can be reused for prolonged time of periods, because they can easily be backwashed, and then they regained their flux, as illustrated by flux recovery ratio in the graph here, that when you increase the nanofiller concentration of the membranes become more hydrophilic, thereby increasing the flux recovery ratio over time after backwashing. And then from there, we also used the humic acid as a foulant model, and you can see that the humic acid fouled the membrane less than the BSA due to its macromolecular structures. And then for the results of the total fouling ratio and the cleanability of the membranes, they resembles the results of the BSA, which shows that as you increase the nanofiller concentration, the membranes becomes more hydrophilic, which increases the likelihood to be used over and over again. But the hydrophobic membranes also suffered from irreversible fouling, which will require excessive cleaning of the membrane, which will increase the overall cost of their application. In conclusion, I can conclude that the composite of amorphous graphene oxide concentration was optimized in the preparation of polyether sulfone mixed matrix membrane, and the performance of the membranes was enhanced. The abundant oxygenated functional groups of the nanofiller composite membranes enhanced the membrane essential properties such as water flux, contact angle. And then the overall humic acid fouled membranes less than the BSA molecule due to size exclusion mechanism, since BSA is a macromolecular structure. And then the fabricated membranes can be used as a pre-treatment for the reverse osmosis in leachate treatment, as they performed relatively well in humic acid, and leachate mainly consists of the organics. Currently, I'm busy with a real sample validation, where I'm taking the real water samples and then filter it using the fabricated membranes, and then from there we investigate the fouling parameters, and then after that I'll perform the membrane autopsy to see if there was membrane degradation, and to see if this membrane they could withstand the long-term use, and also if there was nanoparticle leaching, because there's a major problem with nanoparticle leaching in blending method. And I would like to acknowledge CSIR and INANOS for funding. Thank you.
Thank you so much, Ronewa, for the wonderful talk. Maybe before I open it up to the floor for one or two questions, I just had a quick one. So which of the two, the ion MOF and the ion MOF at Go, which one gave you the best time? Isn't you wanted to develop hydrophobic properties for your membrane? Which one?
We were trying to improve the hydrophobicity of the membrane to make them more hydrophilic, so that they can be more applicable in water treatment. So that, because we need the membranes to be water-liking. So to answer your question, the MOF, it only consists of the hydroxyl and carbonyl groups, which makes it increases the properties, the hydrophilicity of the membranes. But with the composite of MOF and graphene oxide, it has properties of graphene oxide and the MOF, which will give better results, and it also better stability because of the graphene oxide incorporation.
Colleagues, due to time, I think I'll only take one question. If there's anyone who has a burning, there you go.
Oh, thank you. In your technique that you use to stabilize the Fe on the membrane,
Can you confirm whether or not there was any leaching or sludge formation?
Currently, that is what I'm currently doing after validating the real wastewater sample, and then from there I'm going to perform the membrane autopsy to see if there was a leaching of the nanofillers.
Thank you, colleagues, for the wonderful talks. I think I'll leave the floor to the kind gentleman.
All right, another round of applause to Session 4 cohort. I wish to thank Londiwe Mlondi, Mashaule, I think Ronewa, as well as Jacqueline for the presentations. They were well prepared. Personally, I want to thank Londiwe, I see she's not here, for her presentation on sound techniques, because I've realized that whenever my wife speaks, there's cognitive dissonance that takes place. So I was hoping that perhaps I'll be eligible for the middle ear prosthesis trial run. So thank you for the presentations. Thank you. All right, colleagues. Let me also thank our segment leads, doctors. I believe the name is difficult, but let me try. All right, we have Masikole Lugongolo. All right, thank you, and Kelvin Mpofu. All right, these are our doctors and senior researchers within the Future Production Manufacturing Cluster here at the CSIR. A round of applause to them as well. Colleagues, it's 10:55 and we're about to break for the next hour as we are going for the exhibitions and the posters outside. Please make sure that you engage with the researchers. Do ask questions, even if you do not understand. Believe you me, nodding your head does work. And to our presenters, thank you for speaking English. Thank you. isn't it? Thank you. I appreciate the confidence. All right. Allow me then to call upon our GE, Group Executive for Human Capital and Communication, Andile Mabendisa, to come to stage as he will be taking part in the prize-giving ceremony. Allow me then also to request Becky Khatebe, the Director of High-End Skills at the Department of Science, Technology, and Innovation, to join us up front. Let's give him a hand. All right, thank you so much. Ladies and gentlemen, the time has come for me to do the hardest task ever known to men, to read out people's names. If I butcher your name, please forgive me. I think I should take a short course on name pronouncing, just to be sure. All right, drum roll, please. For Best Junior Researcher for the oral presentation, we have Machira Letsualo. All right, please make sure when you come down, you walk with confidence. Machira has set a precedence for us. All right. The smile, don't forget the smile. Thank you. All right, another round of applause. All right, it's in the stride. You know how, you just check how it works and copy him. All right, for Best Junior Researcher for the poster presentation, drum roll, please. And we have Morebudi Motaung. Yes. With a smile. All right, thank you. All right, all right, okay, all right. Listen properly. Best master's student for the poster presentation. Drum roll, please. We have Gugu Ngobese. Thank you for the claps and the smile. All right, we have Best Master's Student oral presentation. Drum roll, please. We have Rachel Brown. Perhaps the clapping is not motivating enough. Is Rachel not here? All right, okay. Let's move on. We have then the next presenter under the Best PhD Student for oral presentation. Drum roll, please. We have Ayomide Abe. not with us in the room, I'll receive their presence on their behalf. All right, let's move. Best PhD student for poster presentation, drum roll, please. And we have Michael Nkoyi. Yes, that's the walk. Right, another round. All right, thank you. Then we have Best Researcher for the oral presentation. Drum roll, please. All right, we have Stefan Karamanski. You can wave, you can wave. Yeah, good. There you go. See, that's how you do it. Thank you. All right, last but not least, Best Researcher for the poster presentation goes to, drum roll please. All right, this could be you, Retabile Mokwena. That's how you do it. All right, GE and my good sir, thank you so much. We're done for now. You may be seated. I almost asked, what does the church say? At this particular moment, as we're about to receive the closing address, allow me to call back on stage and welcome again our GE for Human Capital and Communication, Andile Mabindisa, to the stage.
Right, Program Director, thank you, ladies and gentlemen. Ladies and gentlemen, we've reached the end, right, of our program. Emerging Researchers Symposium 2025. And I would like to take this moment to express my gratitude to everyone for joining us today. Your presence is really appreciated. We had the young researchers who listened to their ideas and innovations. Their passion and creativity has inspired us. Today, we celebrate not only their discoveries, but also the spirit of inquiry that drives them forward, as the CEO said this morning. Let me also emphasize what our CEO stated in his keynote address. Innovation is the driving force behind growth. That is precisely why your role as young researchers is so critical, not just to advance knowledge, but also to ignite progress across every sector of our society. The CSIR has been in existence for 8 years. That is 8 decades of touching lives through innovation. And there's always been an emphasis on growing the set skills, as these are core to the CSR business. And this is in order to stay sustainable and also to continue to provide the much needed technical solutions for the state and also for the industries. More emphasis in the last 30 years has been in ensuring a more diverse workforce, as we've witnessed in the last 2 days. Notably so, in the last 5 years alone, the CSIR has invested just over 70 million in bursaries and also leveraged over 200 million through partnerships with other state institutions nationwide. A number of these graduates, some of you are participating here today, have since joined the CSIR and are contributing immensely to developing innovative solutions that are critical to the country's socio-economic development. These efforts aim to empower you by fostering innovation, entrepreneurship, and skills development. The CSIR views science, technology, and innovation as essential for economic growth and societal advancement. Investing in education, fostering entrepreneurship, and creating employment opportunities will build a resilient and an inclusive economy that leverages on the potential of youth. As the former president said, and I quote, "The youth of today are the leaders of tomorrow." I wish to commend our emerging researchers for their contributions, insightful presentations, and dedication to advancing knowledge today. As they embark on their journey ahead, I extend my heartfelt wishes for continued success, discovery, and impact. Before I get carried away, Program Director, ladies and gentlemen, it is my privilege to extend our sincere gratitude as the EXCO and also as the board. The board was here yesterday. To all that are involved in making this event a success. So first, let me thank all of you for your attendance and all the hard work that you put. Really appreciate it. To the DSTI, Peggy, for your presence and for your support. As always, appreciated. NRF, for your presence as well, and for the exhibition, really appreciated. SASTA, for the generous sponsorship. But more so, I would like to thank the organizing committee that was supported by various individuals from the human capital and also strategic communications. To the various segment leads for facilitating the various segments, really appreciated. And lastly, but not least, to the program director. Thank you very much for the great work. So, ladies and gentlemen, I'd like to thank you, and wish you a great day further. Thank you.
Thank you, Andile Mabindisa, for your closing address. Colleagues, this then brings us to the last part of the program, the part that I think everybody would be excited about, the part where we all go to war. The one announcement that I have is that lunch will be by the deck. All right, lunch will be by the deck. Thank you all for coming. Enjoy the rest of the day. Thank you.